Welcome back to ME 760 Engineering Analysis 1. So last time we studied the orthogonal matrices and we discussed the geometrical interpretation of the geometrical matrices. So let's go on today. I will be discussing some form of matrices like the normal matrices, the unitary, the Hermitian and skew Hermitian, and so on. And we will try to see what's the eigenvalues and eigenvectors for those types of matrices. So let's continue. Just to conclude last time lecture, if we have a vector A and another vector B, and those are two vectors, and A is an orthogonal matrix, and we have another two vectors U equal to the orthogonal matrix applied over the vector A. So U equal to AA and V equal to same orthogonal matrix operated over vector B. Then A dot B, the dot product of the two vectors, A dot V will be just U dot V. So those are U and V are also vectors here in the linear dimensional vector space. So just to prove it, U dot V, if you write those, this is in real space. If you try to write those in matrices form in vectors, U equal to U1, U2 up to UN, and let's say vector V, same V1 up to Vn. So this is in real space. If you want to represent those in matrix form, so you have to take the transpose so that you will be able to perform the matrix multiplication. So this will be U transpose multiplied by V, and U transpose is what from here? Is A transpose multiplied by A, and V is just AB. Then you will take the transpose, so this will give you A transpose, and then the transpose for the vector A multiplied by A multiplied by B, and again you can rewrite this as A transpose, A capital transpose multiplied by A capital B. So what's this? Identity. And this is identity only for what? For orthogonal. And we proved it last time. So this is just A transpose multiplied by the identity matrix multiplied by B, which is nothing more than A transpose multiplied by B, but this is in matrix form, in real space form. This is A dot B. So this is the proof. There is another theorem that states that the determinant of orthogonal matrix is equal to plus or minus 1. The proof, I think we gave it last time, and it is also in the book. And the other one also is the eigenvalues of orthogonal matrices or matrix are real or complex, coming with absolute value of lambda equal to 1. We will be deriving this in a minute in the next topic. So what's the definition of orthogonal matrices? If you remember from last time. What? Yes. So the matrix should not be singular, and A transpose equal to A transpose equal to what? This is the definition for orthogonality. Now, let's look for some other definitions of other form of matrices. So we will be looking for complex matrices. So a complex number usually can be written as z equal to a plus I b, or x plus iy, or whatever. And this is the simple form. And what's the z complex conjugate? It's x minus iy. You can still represent z as r e to the power of what? I theta. Okay, so this is x, this is y. We call this is real, and we call this is imaginary. So number which is x, y in the complex domain, this is x in the real, and this is y in the imaginary, can be represented as r and theta, where x will be what? R cosine theta, and y will be what? R sine theta. So you can represent z as equal to, let's call it r capital so that it will be consistent here, will be r multiplied by cosine theta plus I sine theta. So this is equal to r e to the power of I theta, and from here you can prove that e to the power of I theta is equal to cosine theta plus I sine theta. This is just basic complex number theory. Again, if you multiply z by its complex conjugate, this will give you x plus iy multiplied by x minus iy, and this will give you what? X squared plus y squared, which is what? R squared. So if you take the square root of this, will give you the amplitude of R. So the amplitude, this is just amplitude of R all square. And if we have a matrix A and it is complex matrix, so this matrix, the Aij for this matrix is just the Aij stars. So you'll take the complex conjugate of the elements of the matrix, and this will give you the complex conjugate of the matrix itself. So if you have a matrix, let's say 1 minus I, 5 plus 3I, 2I minus I, 8 I, 5, 6, 7I, and 3I plus 2. So what's the complex of this? This is A. So A complex conjugate is just what? 1 plus I, and this is 5 minus 3I, and this is minus 2I, and this is plus I, and this is minus 8I, 5 is still the same, 6 is still the same, minus 7I, and this is 2 minus 3I. So take the complex conjugate of the elements of the matrix itself, it will give you the complex conjugate of the matrix. So if you take the components, the complex conjugate of the components or the elements of the matrix, it will give you the complex conjugate of the matrix itself. So now let's define one more definition here. This is A dagger. This is called dagger. It's a little bit cross but elongated, and this is, we call it Hermitian conjugate for the matrix, and sometimes we call it the adjoint. And the definition for the adjoint is A dagger is nothing more than the complex conjugate of the matrix, then you transpose it, or the matrix, take the transpose, then take the complex conjugate. So for this matrix A that we just defined, A is 1 minus I, 5 plus 3I, 2I, negative I, 8I, 5, 6, 7I, 2 plus 3I. What do you think A dagger should be? From here. So we'll take the complex conjugate of all the elements, then we will do what? Transpose it. Here is the complex conjugate. Then all what we want to do is what? Transpose it. So this will give us 1 plus I, 5 minus 3I, minus 2I. Then the second row will be now a column. This will be I minus 8I, 5. Then the third one will be 6, 7I minus 7I, 2 minus 3I. So if you take the complex conjugate of all elements first, then you transpose Or if you take this one and transpose it and then take the complex conjugate, it does not matter. It's the same, exactly the same. Any questions so far? Does it make sense for you guys? Okay, so for Hermitian conjugate or adjoint, it has the following property. The property is, if you have A, B, C up to G, and you take the Hermitian conjugate, the adjoint, it will give you the last one first, then will give you the rest, C, B, then A. And you can take this as exercise, try to prove it. Again, we have X equal to X1, X2, up to Xn. What do you think X dagger or the adjoint will be? What? So transpose this. It's a column. It's a row. And then do what? Take the what? Conjugate. So this will be what? That's it. Easy. So let's define some special matrices, special types of complex matrices. So let's start clean. So one of those types of matrices is called the Hermitian matrix. So just differentiate between Hermitian matrix. Guys, I want you to focus. Differentiate between Hermitian matrix and the Hermitian conjugate or the adjoint. Hermitian matrix, I will define it right now. Hermitian conjugate or adjoint is A dagger, and you take the transpose, then you take the complex conjugate for all the elements, or vice versa. But what is the Hermitian matrix? The Hermitian matrix is a matrix that's defined as the matrix A is equal to its Hermitian conjugate or adjoint. And this is just, and in this case you will have Aij dagger will be equal to Agi star. Yes, because the matrix A, let's assume that it is A11, A12, 3 by 3, let's say A13, A21, A22, A23, A31, A32, A33. Then what's the Aij here? Let's take the A dagger would be equal to what? So transpose it first. So it will be A11, A12, A what? 13, and then 21, 22, 23, then 31, 32, 33. Yes? Then you will take what? You will take the complex conjugate. Yes, guys? If I tell you now that those two matrices are the same, what does it mean two matrices are equal? This one is equal to this one. So Aij, let's say Aij, so Ij, and this is equal to what? Aj asterisk. Yes? Yes, guys? So Aij equal to Aji for this matrix. So here, just do it like this. So what does it mean if you have an element of the matrix equal to the complex conjugate?
Real.
Yes, real. Yes? So this entails that the diagonal elements must be real. Because the diagonal is still the same. Yes? A22, A11, A22, A33. And the diagonal element is what? Still the same, but this is just for the diagonal. For diagonal, if you take the diagonal and you take the dagger of the diagonal, you do what? A11, the dagger of the diagonal, means transpose it, it's a number, so transpose it number, this is the same. Take the complex conjugate, so it will be Aij will be Agi or Aij, Agi, and it is the complex conjugate. So it must be real. And this Hermitian matrix is just a generalization of real symmetric matrix. Why it is generalization of the real symmetric matrix? What's the definition of the symmetric matrix? A transpose equal to what? A. Yes? So let's assume the matrix is real. So if I take the complex conjugate for both, okay? What's this? A transpose, then you take the complex conjugate. This is what? A dagger. Yes? And A transpose, complex conjugate for a real matrix will be what? Will be A. So the symmetric matrix for a real, if the matrix is real and it is symmetric matrix, this is a special case of what? It's a special case of what? The Hermitian matrix. So if you have a Hermitian matrix, usually Hermitian matrix are class of complex matrices. But let's say that I have a Hermitian matrix, for example, and its components or elements are real. So it will be symmetric matrix. The second type of matrices are called the anti-Hermitian. What do you expect the anti-Hermitian will be? What do you think the anti, or sometimes they call it skew Hermitian? Come on, guys. What do you expect? Equal to? Huh? Negative A. And again, what's the condition for this one? For the diagonal. So the diagonal Aij, if you take the dagger or the adjoint, would be equal to what? Negative AGI of the complex conjugate. A number equal to negative its complex conjugate. What's this number should be? Nope. A number equal to, if the number equal to x, it's okay. Okay, 0 or pure imaginary. Yes? So if you have negative 3j, this is the number. Let's say z. And what's z prime? D star? Plus what? So when z equal to negative z equal to negative z star, it means that the number is what? Purely imaginary. So this is, the diagonal should be what? Should be or must be 0 or purely imaginary. And this is a special case of what matrix? Huh? The anti-Hermitian is the skew symmetric is a special case of the anti-Hermitian. Yes, because the skew symmetric is what? A transpose equal to what? To A. Again, if you take the complex conjugate for both, and if the matrix is real, so this will give you what? So this is for real skew symmetric matrix. So we define what? We define the complex matrix, we define the Hermitian, and we define the anti or skew Hermitian, and we show that the symmetric and skew symmetric are just special cases for a real matrix for the Hermitian and anti-Hermitian. So now we will define a matrix called unitary matrix. And the unitary matrix is just defined as the Hermitian conjugate, instead of equal to the matrix itself, is equal to the inverse of the matrix. And this is generalization of what matrix? What can be generalized to these types of matrix? Orthogonal matrices for real matrix. Real matrix is a special case. So if your matrix is real, so what will happen for the A dagger? A dagger is equal to what? A transpose for what? For real what? For real matrix. And in this case, if you have a real matrix, A dagger equal to A transpose. So in this case, A transpose will be equal to A minus 1, and this is a definition of what? Orthogonal matrix. So just if you have a real matrix, the unitary matrix will be just what? The orthogonal matrix. And let's define one more matrix. And this matrix is called the normal normal matrix. And the normal matrices are those matrices that will fulfill the following: A dagger is equal to A dagger A. So they commute. So we knew that matrices do not commute. AB is not equal to BA. Yes? But for those normal matrices, they commute. A multiplied by the adjoint or the Hermitian conjugate is equal to the adjoint or the Hermitian conjugate multiplied by A again. And we will note here that the unitary Hermitian and skew Hermitian are normal matrices. So you can go back and do the exercise, and you will notice that all those types of matrices, unitary, Hermitian, skew Hermitian, are normal matrices. Okay, guys? And the special cases also are normal matrices. What are the special cases of the unitary, orthogonal, Hermitian, symmetric, skew Hermitian, skew symmetric? So those 6 types of matrices are what? Normal. What does mean normal? I can commute those matrices. Okay? So you can commute those types of matrices. So we will be now looking for the eigenvalues and try to see what's the properties for the eigenvalues for those types of matrices. So what's the definition for the eigenvalue problem? Matrix A operated over a vector X will give me a number which may be a complex or real operated over or multiplied by the same vector here. So the general properties: if X is an eigenvector, then alpha constant multiplied by the eigenvector will usually be also an eigenvector. And usually you pick alpha so that when you pick alpha so that the product of the vector will be equal to and again you can substitute here alpha x and alpha x here. Alpha will go outside, so you'll have alpha multiplied by a x, and here is alpha lambda x, so alpha will cancel out and you will end up with ax equal to lambda x. So still the same, alpha x is an eigenvector for the same eigenvalue problem. Second property, if you have ax equal to lambda x, you have an eigenvalue problem. Then if you multiply both sides by the inverse of the function, so this will give you a inverse multiplied by a operated over x equal to lambda a inverse operated over x. What's this? I. So this will give you what? This will give you A inverse operated over X equal to 1 over lambda multiplied by X. What does it mean? What does it mean? Same eigenvalue problem, but instead of the operator is the matrix X, it's now the matrix what? Matrix A. It's matrix A inverse of the matrix, and I will have the same eigenvectors. So the eigenvectors are what? Are the same X. But now for the inverse matrix, the eigenvalues are no longer what? Lambda, but the inverse of what? Lambda. So for a matrix A, you will get the eigenvectors are X and the eigenvalues are what? Lambda. For the inverse of the matrix, you will get the same eigenvectors, but the eigenvalues are what? Are inverted. Okay, the inverse of this. So A minus has same eigenvectors and 1 over lambda for eigenvalues. So let's try to see what are the eigenvalues. So this is some properties for the eigenvalues. So a theorem states that for the eigenvalues, they are either real for Hermitian matrix, or they are imaginary, or zero for a skew Hermitian, or they are eigenvalues, the absolute value, if they are complex, will be equal to 1 for unitary matrices. So let's try to prove it. So if I have the eigenvalue problem, A operated over X is equal to lambda X. Now, if I multiply both sides by the adjoint, X dagger, both sides. So this will give me X dagger A multiplied by X is equal to X dagger lambda X. And I can take lambda, so this will be lambda X dagger X equal to lambda. What's X dagger X? X dagger is what? X1, X2, Xn. And what's X? X1, X2, Xn. So what's X dagger X? Something you multiply it by its complex conjugate. ZZ star is what? The amplitude of Z. So this is square. So this will be what? X1 what? Square plus what? X2 squared up to Xn squared. This is what? If you have square number, square number, square number, square number, so this is real, and it is what? At the end is what? All this is what? Positive number. Yes? Real positive number. Now, I can write lambda I can write lambda as x dagger A multiplied by x divided by x dagger x. We knew that this is what now? Real number. This, we call it form. So now, let's try to see for all the three cases here, for real, for Hermitian, anti-Hermitian, and unitary. Okay? So one for Hermitian. Let's look for the form for a Hermitian matrix. So what's the form? X dagger AX. Okay, guys? A vector X dagger, the adjoint AX. What's AX? Matrix multiplied by a vector will give you what? A vector. Yes? Any vector. Vector multiplied by a vector will give you what? A number. Yes? Vector by a vector is what? A number. So this is what? Number. Maybe a complex, because this is complex. Maybe it's a complex number, or maybe it's a real number. So if I take the transpose for this number, did I do anything? It's a number. 3, if you take the transpose of 3 is what? 3. Take the transpose, it will be like this. Or 4, take the transpose, it will be like this. Same number. Yes? I'm joking. Yes? Yes, guys? So if you take the transpose of a number, it will give you a number. So now, so A adjoint multiplied by A multiplied by X. Now, if you apply the transpose property, this will be what? So X dagger is just equal to what? X transpose, and then this, which is equal to what? Yes? So if you take the transpose of this, this will give you what? X star. Yes? A transpose, and this will give you what? X transpose. Yes, guys? Yes? I can rewrite it as X transpose, A transpose, and this. Now, if my matrix is Hermitian, what does it mean, Hermitian matrix? Hermitian, A dagger equal to what? A. Yes? A dagger is what? A star transpose. So it will be A transpose all star equal to what? A. If you take transpose for both sides, you will eliminate the transpose from here and you will make it here. Yes? So for a Hermitian matrix, I can remove A transpose and I can put what? A star. So this will be X transpose, A star, X star. Okay, guys? If you take the transpose out, so you will end up with what? X. If you take the transpose, it will be X transpose. A, if you take the transpose, it will be A transpose. X transpose, sorry, complex conjugate. X transpose, if I take the complex conjugate of X transpose complex conjugate, will give me what? X dagger. So now, a number equal to its complex conjugate. This is the number, X transpose AX equal to its complex conjugate. What does it mean? The number should be what? Real. So in this case, this is a real, and this is what? real positive, and this is the real positive. Yes? So in this case, lambda is what? Real. So for Hermitian, the lambda is what? Real. And this is the proof for the Hermitian. Let's give you the proof for the anti-Hermitian. Anti-Hermitian will be straightforward, guys. Yes? Why? What do you think? What you will change here? The only thing that you will change here, this is exactly the same. I will take the form. The only thing I will change is when I will say that this is anti-Hermitian, so this should be what? Negative here, negative sign here, and it will end up with negative sign here. A number equal to its negative of its complex conjugate. Yes? So lambda will be what? 0 or pure imaginary. Yes? Lambda will be what? 0 over real is 0. Pure imaginary over real is what? Is pure imaginary. And this is the proof for the second one. Imaginary for a skew symmetric or a skew Hermitian, it's a pure imaginary. Now we'll come up to the last one, and the last one for unitary. So for unitary, if we take AX equal to what? Lambda X. Okay, guys? And I take the adjoint. The adjoint is just transpose and then take the complex conjugate. So when you take the adjoint for a number, it will give you what? The complex conjugate. So this is call it 2, and this is call it 3. If you multiply 2 by 3, this will give you what? AX adjoint multiplied by AX, and this will be lambda complex conjugate multiplied by X. So what's this? The amplitude of lambda. And now I can take this, and if I multiply both, this will give me what? Those two. X adjoint A adjoint multiplied by X. So what's A adjoint for a unitary matrix? Unitary matrix, A adjoint is equal to what? A inverse. So this will give you this. A inverse multiplied by A is what? Identity. So this will give you this equal to what? Lambda square multiplied by this. So what's lambda square should be? 1. So lambda square should equal to 1. And in this case, this is the condition for unitary matrix. So next time I will stop here, and next time we'll give just a theorem that the eigenvalues for a normal matrix A are the complex conjugate of the eigenvalues for A dagger. So if you have a normal matrix A, and this matrix is normal, and you take the adjoint of this matrix, for example, so the eigenvalues for this matrix, eigenvalues for this normal matrix are the complex conjugate of the eigenvalues of this matrix here. So we will deduce it next time. So do you have any questions? Okay, if not, we'll see you next time. Thank you so much.